there are different types of equations that we now need to address. There are three types. There are molecular equations, ionic equations, and net ionic equations, okay? So the first one that I want to look at is a molecular equation. So this equation here is a molecular equation. It shows the complete neutral formulas for every compound in the reaction, okay? So we can change this. We can change this and make it appear as a complete ionic equation. So a complete So it's basically going to be each of these compounds broken down into substances. But you'll notice that on these polyatomic ions, we're leaving these together. These always stay together, right? So when you write your complete ionic equation, you always want to write your charges for your substances. You can be counted off on that. But complete ionic equations just show the reactants and the products as they are actually present in the solution, right? So rather than showing them as a compound, it shows them as individual elements as they would appear in a solution. So that would be a complete ionic equation. All right, guys, so in this equation, I have written out a full equation. It's taken up 2 lines, I guess, because I write too big. But I have circled your nitrate, your sodium, and your nitrate. The reason why I've done that is because these are spectator ions. So these ions remain the same on both the product and the reactant side of the equation. So they don't change. They don't go through any kind of chemical reaction. The ones that do, the elements that change are the sodium and the chlorine, right? So spectator ions do not participate in the actual reaction, right? So you need to know this because your professor on a quiz or an exam may give you an equation and ask you to identify the spectator ions, okay? So the reason why we know that these substances, the sodium and the nitrate, don't participate in the reaction is because on the reactant side, they're aqueous. On the product side, they're aqueous. Whereas the silver and the chlorine are aqueous on the reactant side, but when they react, when they come together, they form a solid. So they do participate in a reaction, right? So that is how we know how to identify our spectator ions. We take a look at our elements here and what their states are on the reactant side of the equation and on the product side of the equation. Okay? So we can actually simplify this equation and all of our spectator ions can be omitted. And we can actually rewrite this equation and it'll appear like this. So this eliminates all of those spectator ions. And this is actually referred to as a net ionic equation. So I just wanted to point that out, point out the three different kinds of equations: the molecular, the ionic, and the net ionic, or the total ionic equations and the net ionic equations. So you guys need to be able to do these. You need to be able to identify your spectator ions for quizzes and exams. The next thing that we're going to talk about are acid-base and gas evolution reactions. Okay, so in acid-base reactions, and we'll take this one for example, this is a combination of hydrochloric acid and sodium hydroxide. So our hydrochloric is our acid, our sodium hydroxide is our base. And so what happens is this hydrogen from our hydrochloric acid combines with our hydroxide to form water, right? And so then our sodium and our chlorine come together to make our salt, right? So that's how we know this is an acid-base reaction, because when the acid and the base are mixed, when the solutions are mixed, the two aqueous substances are mixed, they created a ball of water and a salt. Now, acid-base reactions are also called neutralization reactions because they generally form water and an ionic compound. And so salt, in this case, the sodium chloride, is the ionic compound. Another acid-base reaction would be this one. It's going to be H2SO4 plus potassium hydroxide to produce water and salt. So here we are with our acid and our base and our water and our salt. We need to spend a little bit of time on gas evolution reactions, and the reason why is because when you have a problem that is a gas evolution reaction, depending on what substances are involved, there's always an intermediate product, right? So if you look in your textbook, there is a table that shows the intermediate products for certain combinations. Like for sulfides, there is no intermediate product, but the gas that is produced is dihydrogen sulfide, right? And then you have carbonates and bicarbonates. They produce an intermediate product of H2CO3. So when we are working with that type of a gas evolution reaction, if we produce an intermediate product of H2CO3, we know that it's going to break down even further. And I'm getting ready to demonstrate that for you here in just a moment. But I need to point you to table 7.4 in your textbook, page 227. Your professor has probably also put this in their lecture notes. So you need to get a flashcard because you will be expected to memorize those products. So in this particular gas evolution reaction, we have a hydrochloride and a sodium hydrocarbonate. When they come together, they form H2CO3, so dihydrogen carbonate, I think that's right, plus sodium chloride. Because we memorized that table, we recognize H2CO3 as an intermediate product of this gas evolution reaction. So we know that H2CO3 breaks down further and produces water and carbon dioxide gas. So liquid water and carbon dioxide gas. Our sodium chloride stays the same, so it just drops down as part of our final product. Okay, so this is the only thing that changes here, is this intermediate product, the H2CO3. So this is a gas evolution reaction. So chemical reactions. So there are several different types of chemical reactions that we need to be able to identify for Chapter 7. And what I've done is I've written some of those down, and they're generic equations. Now you will see these on a quiz, you'll also see them on an exam. So this is a great time to grab that flashcard and write this information down, or put it in your notebook. Whatever you use to study that works for you, you need to make a special note of this. So a synthesis reaction is where you have two elements that come together to form a compound. A decomposition reaction is where you have a compound that decomposes into two separate substances, maybe more than two. A single displacement reaction is where you have a single element and a compound element that react together and create a new compound and a new element, a new single element. And then in a double displacement, all of your compounds switch partners, right? So it's kind of like a square dance. So you have your AB plus your CD, which are your two compounds. And so A and B switch partners with C and D. And so the new products are AD plus CB. Kind of confusing, I know, but you need to know this information, all right? We're also going to, I'm going to put a couple of chemical reactions on the board, and we're going to work through identifying those. Okay, so I've put a couple examples up here. This is the type of equation you might see on a quiz or an exam and be asked to identify it as a synthesis, decomposition, single displacement, double displacement. You may be asked if it's a redox reaction, which we'll talk more about those in just a minute. So for this first one, pretty simple. You look here, you've got your two compounds. They come together to form one compound. This is a synthesis reaction. And so if we were asked what the generic formula was, it would be A plus B yields AB, right? And then looking at this, the second one, this is a decomposition. We know that right off the bat because we have a compound that's decomposing and producing two new elements or compounds. So this is a decomposition. And the generic equation is AB yields A plus B. Okay guys, so we have oxidation reduction reactions. They're also known as redox reactions. This is noteworthy information, so you might want to jot this down. So redox reactions involve the transfer of electrons. Most redox reactions involve the reaction of a substance and oxygen. This is not always the case. Oxidation and reduction must happen together. You can't have one without the other, okay? And if you ever are in doubt, just remember oil rig. Oxidation is the loss, reduction is the gain. Oil rig. All right, so let's take a look at a few equations and identify them as redox reactions, or it could be an acid-base reaction. So let's take a look at a couple of different equations and see if we can't identify the loss of electrons and the gain of electrons. You may be given equations like this on a quiz or an exam, and your professor may ask you to identify the type of reaction that has occurred. Okay, so let's take a look at our first reaction. So we have magnesium and oxygen that combine to create magnesium oxide. Would this be a redox reaction? And the answer to that question is yes, because Well, it fits the rule. So redox reaction is a reaction with an oxygen, an elemental oxygen, which that has occurred here. But as you can see from C, this is a metal and a non-metal. There has been an exchange of electrons. There's no oxygen involved, but it is also a redox reaction, okay? So we have a redox reaction for A and a redox reaction for C. So how do I know this? So on your periodic table, you have been asked to identify the charges of each group of substances, right? So we can look at our magnesium. We know that our magnesium is a +2 charge, right? And we know that our oxygen is a -2 charge. So when they combine, magnesium transfers 2 electrons to the oxygen to make it a neutral compound, okay? Oxidation is the loss, reduction is the gain, okay? In the second equation here, this is not a redox reaction. This is actually an acid-base reaction. Because if you look here, we have hydrobromic acid. So here's our acid. Then we have calcium hydroxide, which is our base. They combine and produce water and calcium bromide. Calcium bromide. So it creates a water and a salt. So this is an acid-base reaction, not a redox reaction. C, we've already identified as a redox reaction between a metal and a non-metal. D is a redox reaction. It is indeed a redox reaction. We have zinc, and then we have iron 2. Okay, so it's iron with a 2+ charge. Our zinc is also a +2 charge. This is a redox reaction because there is a transfer of electrons. So our iron transfers these 2 positive electrons to our zinc and makes the zinc a 2+ charge. Yes, that's right. So these are the type of equations that your professor might throw at you and ask you to identify redox reactions. But just always remember for redox reactions, oil rig. You'll talk more about that in lab. You'll get more practice with these in lab. My recommendation would be to write your charges above your elements here or your compounds, and that way you can easily identify where the reduction occurs and where the redox reaction occurs. The loss of electrons and the gain of electrons. Alright guys, that's going to be it for this video. Like I said, I was trying to keep it short since all the other ones have been fairly long, like an hour long. Really sorry for that. Our next video is going to be over Chapter 8 and part of Chapter 13, which gets us into stoichiometry. It's going to be involving a lot of mass-to-mass conversions. So it's going to go back to what we learned in Chapter 5. And so we're going to be reintroduced to the mole. We're going to be using molar mass more. So you definitely want to have your calculator and your periodic table handy because we will be referring to it a lot. So check back in the next day or so, or in the next few days, or just check the YouTube channel for another video covering Chapter 8 and part of Chapter 13. And as always, stay safe, stay healthy, and I'll see you next time.